Alright class, so we're into the second part of probability, and again, it's just a little bit that we need to know so that we can understand some of the stuff we're going to be doing, and this is some stuff that we need to know before we can get into the two proportions notes. So we're going to look at things just from a contingency table perspective, just because that's what we're going to see things from. And so when we have this contingency table, we're really going to be looking at two variables, and they're both going to be categorical. So for example, we're going to look at the type of twins, whether they're fraternal or identical, and then the gender of those twins. So the gender options with either they are both boys, both girls, or one boy and one girl. So we're first going to talk about reading the values in the table to understand things here as well. One thing that's not always given to us in the table that I'm first going to actually create here are totals. So I'm going to add some totals here. So this could technically be where it actually says total. And we'll do the same thing over here as well. So I'm just going to start by adding up the 28, the 52, and the 90 to get me the 170, and the 79 and 101 to get me 180. This time I'll be adding my columns, so going down here. This will be 107, this will be 153, and this will be 90. And then I can find the overall total as well by either adding up all all 6 numbers inside the contingency table, my 2 row totals, or my 3 column totals. I can get that 350. So we're going to talk about reading these numbers, and there's a few different types of numbers that we're going to talk about here. So let's first talk about what this 28 would represent. So what this means for us, that this 28 means there was 28 sets of twins that were both boys and were fraternal. So we'll put this together of twins were fraternal boys. And so what I look at with these numbers on the inside is they tell me what type of twin they are and what gender they are. So, right, it tells me about both of my variables. It tells me about type and it tells me about gender. Next, let's talk about one of these row totals. So let's talk about the 180. So our 180 here, so 180 sets of twins were identical. And what we'll notice here is I'm just told about the type of twins, but nothing about the gender at all. Now let's talk about one of these column totals. So like for example, this 153 would just tell me 153 sets of twins were girls. So it only tells me about gender, but nothing about the type of twins that we have. And then finally, let's talk about this 350. That just told us our total number of twins sampled. But it doesn't tell me anything about the type or the gender. So in a sense, this is my overall sample size. So first, making sure we feel good about reading the table. We're going to relate this now to probability by talking about some definitions here. So when I talk about an event A, this is determined how we do it, is looking at a specific row or a specific column. Not looking at both, but just looking at one or the other. So for example, I might just record boys as being an event that I'm interested in. And so then if I wanted to find the probability of having both boys That's just going to be the total number that we're both boys. So that's our 107. So notice that's just our boys column total over my entire sample, which is 350. So giving us a probability here of a little bit more than 30%. I could also just look at a specific row. So my other example, we could just have be identical. So then the probability of being identical twins would be the number of twins that were identical. So this would be our 180 over our sample size of 350. Or a little bit more than half were identical. So an event is just looking at one specific row or one specific column and finding its probability. We also have what's called a union of two events. And how this can be thought of is A or B. But I like to add that this does actually include both as an option. So for example, when you go to Olive Garden, they might ask you soup or salad, but you're only allowed to choose one. So when we talk about a union here, it does actually include the option of both of those things at the same time. So to understand this, for example, let's use the two that we have above of boys and identical. So if I wanted to find the probability of boys union or identical, they either are going to be boys, or they're going to be identical, or they can be both. So what that means is I'm going to have anything that's in boys column, anything that's in identical, and kind of add them together. So it's going to be this 28, this 79, this 101, and then technically the 0, even though it doesn't add things. I'm just going to add those three numbers together here. So we'll take the 28 plus the 79 plus the 101, still out of our 350. Oops, I'm sorry, that's a little messy. So a little shy of a 60% chance here. The next type of event we want to talk about is an intersection. So this means A and B, so it has to be in both things at the same time. Some notation you might see for that is this upside down U is an intersection sign if you've never seen that before. But this has to be in both. So it has to be in both. So intersection, what's really nice about contingency tables is it's just where they intersect. So if I wanted to find the probability of being boys and identical, or that intersection here, it's going to take my boys column, my identical row, and figure out where do those intersect. Well, it's just that 79 on the top out of our 350 that we sampled. Which was a little bit more than a 22% chance. Another type of event is called a complement, which is read as not A, or sometimes known as A with this little C superscript. You also might see A prime, for those of you that have seen that before, or A bar. So some other notation someone you might have seen be A prime or A complement, and there's other different ways of writing that. And what the complement is basically the opposite of. So it's sort of what's left over. So like if you complement, you usually kind of make up for what's missing. So let's do one here and see if that makes sense. So if I wanted to find the probability of boys complement, basically that's anything but being boys as gender. So that's going to be being girls or being one of each. So it's going to include anything that's not both boys. So I'm going to take all the girls and all the one of each and add those together. So it's going to be 153 girls, the 90 of one of each. And notice I just used the column totals there to make my life a little easier. over the 350. Which gives us a little shy of a 70% chance of that happening. Or another way to do it, so I could say the probability of B complement is actually just 1 minus the probability of B. And notice we already have the probability of B up here. So you'll notice that's just 1 minus our 0.3057. Another way to get it. So complement basically means anything but that. Right, now to a little bit more specific type of event that we see a little bit more often is what's called a conditional. So first, notation-wise, because you will see me write something like this, this is read as A given B, or this is the probability of A given B. So what this actually means is if B has already happened, what is the probability of A? That's what we're trying to find. So we already know something. So that's something that's a big thing to understand here is it limits your possibilities. So let's see this by an example and see if that helps some. So let's talk about the probability of being boys given you're identical. Now one thing you'll see here is I actually give you formula-wise, that those of you took like a stat 113 or a stat 250 will understand this formula. But I think this is much easier just to understand without even having to use the formula, especially from a contingency table perspective. What this means, I know that the twins are identical. So if the twins are identical, what's the probability that they are boys? That's sort of what I'm asking here, if they're identical. So what I'm going to do when I calculate this probability, on the bottom is how many identical twins were there. Well, what I can see is, well, there was 180 sets of identical twins. So I can't use this 350 on the bottom anymore because it can't be any of the sets of twins. I'm only talking about those that are identical. So what I'm going to see here is that my bottom number is going to be 180. How many twins were identical? Now that I know they are all identical, how many of those identical twins are boys? Well, it's just that 79. So when I actually calculate my probability here, it's just that 79 out of the 180. And this is where you see how it limits the possibilities. I no longer have that 350 on the bottom. It has to be identical twins now, which is kind of reducing it down to that 180 that's on the bottom. And so this would be approximately a 44% chance. Or how I can think to write this, 43.89% of identical twins were boys. Just to make sure it's for full understanding, I'm actually going to flip that so you understand that it really actually is different. Because if instead all I did was flip my I and my B around, it's a different calculation I have to worry about. Because this now is saying, okay, I know that I had boys. That's what I know about them. Now, what is the probability that those are identical twins? So I already know they're boys. What's the probability that they're identical? So when I'm talking about my bottom number, how many sets of twins that I had were boys? Well, that's 107. That's going to be my new bottom number. Now that I know, okay, I'm looking at the 107 sets of boy twins, how many of them were identical? It's 79. So calculation-wise here, we get 0.7383, which notice is very different than the other one that we found. So if we write out what this technically is, this means that 73.83% of boy twin sets are identical. So notice how flipping that of which one we know actually does change our interpretation. So a conditional probability is one that we talk quite a bit about. We have two different special types of events that we're going to talk about here. The first one is what's called disjoint or mutually exclusive events. Those are the same term, disjoint or mutually exclusive. What that really means is they have no outcomes in common. Basically, they can't occur at the same time, or the probability of both of them happening at the same time is 0. And we have a great example with our contingency table. So where I can see I'm going to have an intersection of 0 is right here. That is, I can't have identical twins and have one of each gender. So I can't have a boy and girl who are identical twins. It's not possible, can't happen. Those are disjoint or mutually exclusive events. So how I could write that here is the probability of being identical and one of each, because we haven't defined that one yet here, is 0. And that this hopefully makes sense because you can't be identical twins where you have one boy and one girl. Right? That's not a possibility. So that's just what it means to be mutually exclusive, is you can't happen at the same time. Very nice, very easy to see. A little bit one that's harder to see is independent events. So that's defined here that the outcome of one event has no impact on the probability of the other independent events occurring. So if they're independent, the one does not affect the other. So first let me write that out in a little bit more terms. So knowing additional information doesn't change anything. That's what it would mean. So what that would mean for what we're looking for is if I were to calculate a conditional probability of A given B, knowing B would not have any effect on things. So if I know B had happened, it has no effect. That's what it's going to mean to be independent. So if they're independent, the probability of A given B is just the probability of A. Now first, it's a hard thing. You can't just see it. You can't really just see if things are independent. We really do have to check them to see if they're true. But here's sort of a simple idea that helps. So example, suppose we're doing 2 coin flips. And I ask you to find the probability that there's a heads on the second flip, given that the first flip was heads. Does what happened on the first flip affect the second flip at all? No, they're independent events. This is really just the probability of being a heads on the second flip, which is 50%. So knowing the one thing does not impact the other at all. Now notice we didn't use a lot of these rules. I just have these on there for those of you that have seen them before. The biggest thing we're going to focus on here is making sure we understand the difference between a conditional probability and an intersection. Those are probably the two that students confuse the most. So we will talk about those as a difference in our examples that we look at here. And then also the big idea of independent events is going to show up for us. So let's go ahead and do an example. So we're going to look at gender and ice cream preference between vanilla, chocolate, and strawberry ice cream. I know it's not very exciting, just an example to work with here. So we're going to first find the probability that a randomly chosen person prefers strawberry ice cream. But one of the first things I'm going to do here, I'm going to put my totals in here. Because I'm going to need them anyway, so I might as well get them. So I'm going to add up all my men. Going to add up all my women. Going to add up all my vanilla, chocolate, and strawberry. So I have all this. So if I want to find that a randomly selected person prefers strawberry ice cream, it's going to be how many people preferred strawberry ice cream and how many total people did we sample. There's going to be about a 20% chance that someone preferred strawberry ice cream. So there's a probability of an event. What is the probability that a randomly chosen person is female? Now notice that we said randomly chosen person. So we're still looking at all of my 525. How many of those were female? 270. So it gives me a little bit more than a 51% chance of that happening. Now we'll get a little bit more complicated. What is the probability that a randomly chosen person is female and prefers chocolate ice cream? Well, I know I'm looking at two different things. I'm finding female, chocolate. That's where sometimes we get confused on what symbol needs to go here. So I'm actually going to jump to already think about the calculation here. We're trying to find the probability that a randomly chosen person. So we're starting with all 525 people. So we're really trying to find the probability that any of our people are female and, which is our intersect, chocolate. So we're going to go up here to where my female is, where my chocolate is, where do those intersect. That's my 135 on the top. Now let's see how D reads a little bit different. What is the probability that a person who prefers strawberry ice cream is female? Who are we starting with? Probability that a person who prefers strawberry ice cream. Well, how many people preferred strawberry ice cream? So 105 is what goes on the bottom. Now, of those 105 people, how many of them were female? Well, that's just going to be my 80 on the top. Now, what did I just find? I found the probability that given you like strawberry ice cream, so that's what goes after the bar there, what is the probability that you are female? Which turned out to be a little bit more than a 76% chance. Are the events being female and preferring strawberry ice cream mutually exclusive? So if they were mutually exclusive, that would mean that the probability of being female and liking strawberry ice cream would have to be 0. Is that the case? No, right? We have females who preferred strawberry ice cream. So they can't be mutually exclusive. Now, are the events being female and preferring strawberry ice cream independent? All right, so what would it mean if they were independent? Well, if they were independent, and I'm going to use the one that we already found. So we found the probability of female given strawberry ice cream. So that would mean the probability of being female given you like strawberry ice cream would just be the probability of being female. And this is what I'm going to check. Well, we already found the probability of being female given you like strawberry ice cream was 0.7619. We also already found the probability of being female, that was part B, was 0.5143. Are those two numbers equal? Nope. They are not independent. So knowing that you liked strawberry ice cream did actually change the group of people we were working with. There were going to be more females that liked strawberry ice cream than there were just females. Okay, what is the probability that a randomly chosen person does not prefer chocolate ice cream? So here we're being asked to find the complement of chocolate ice cream. So this would just be any of those that preferred vanilla, the 160, or the strawberry. So I can just take the 160 plus the 105. And we started with a randomly chosen person. So we're out of our 525 here. So we get a little bit more than a 50% chance. And finally, what is the probability that a male prefers vanilla ice cream? Well, we're not talking about a randomly chosen person, probably that a male. So first, how many men were there? 255. So that's my bottom number. How many of those men preferred vanilla? 105. So that's going to be our top number. Which is a little bit more than a 41% chance. Now, how would I actually write that? Given that you are a man, what is the probability you prefer vanilla ice cream? Okay, so there's an example that I did. I want you to pause the video here if you're feeling uncomfortable with this and try the next example on your own and then see if our numbers match. Okay? Alright, so comparing our answers, so first I created all of my different totals here. The probability of not being black I found in the two different ways. I did just like the complement rule, so this is the probability of being black. I took 1 minus it. Or you could take the number of white plus the number of others and divide that by the total. The second one asked for the intersection, so we start with the total of the 2533 drivers. 293 of them were white and had a search, so a little bit more than 11% chance. When you come up with mutually exclusive events here, basically you can't be in two different rows or two different columns at the same time. So for my example, I said, well, you can't be both black and white, right? You have to be the one or the other sort of category that we had there. So you can have, you can't be searched and not searched, right? So those are kind of mutually exclusive events. Find the probability of search is just the total number of searches over our total sample size here. E is sort of nice to just kind of first think about what it means in words. So if search was independent of race, that would mean that your race would actually have no impact on the probability of search. So your race was not influencing being searched or not. So what that would actually mean is the probability of being searched if you're black would be the same as the probability of being searched as if you're white, same as the probability of being searched if you were other ethnicity which would just be your overall probability of being searched. That's what independent would mean here. Here I actually calculated that, so the bottom number is always just the total number of that race we had. So we had 1,600 people that were black sampled, 887 whites, and 46 that fell into an other category. And then on the top were the number of those in that row that were searched. And so our probability of being searched if they were black was almost 51%. Being searched if you were white was about 33%. And being searched if you were other was about a 41% chance. Those are calculations. These other two questions are more for you to think about it. So look at one concern here. This is kind of how we might use our data to answer a question. So one of the concerns was where black drivers were being stopped more often. And do you think that is actually the case? So this is actually just ignoring search. Because if you look at, we had 2,500-ish samples here. 1,600 of those were black. So about 63% of all the people stopped here happened to be black. And so some people will look at that data and already be concerned. Well, what it matters is where did we sample in Cincinnati, right? We don't actually know the race breakdown of where the sample was taken. Because, for example, if you were in like my hometown that I grew up in, we're probably about 75% white. So if 60% of the stops were black, I would definitely be concerned that black drivers were just being stopped more often. But if you were in an area that's like 60% black, the fact that 63% of all drivers stopped were black would probably not be that surprising to us. So you want to know more about the makeup of your population to really know if that should have been a concern. Other things for you just to thinking about, if there's other questions that looking at this data might bring that we could actually be testing as well. Sometimes once we start looking into the data, it makes us want to ask more questions. But again, so the big things to take away here is the idea of independent, because we're going to be testing that as we get going as well. Conditional probabilities. Those are going to be our two big things you see here, independent and conditional probabilities.